Thank you very much for the introduction. Well, I would like to thank the organizer for this invitation. Actually, I feel very honored of giving this seminar. This One World seminar is a great idea, and I've been watching many very interesting lectures so far. Well, actually, I believe it's time to reduce our carbon impact and rely on more advanced technology, and it's a very good step in this direction. So today I'm going to speak of stability in Gagliardo-Nirenberg inequalities. And well, here is essentially the outline of my lecture. So the goal is to provide a constructive result on the stability for some Gagliardo-Nirenberg inequalities, and I will explain a bit more what we exactly plan to do. And the main tool for this approach is going to be the fast diffusion equation and entropy methods. So I'm going to detail a little bit and start with Rényi entropy powers. Rényi entropy powers is a good way to understand the Carré-Duchamp method and how this works. And then go to the entropy-entropy production inequality, which is actually equivalent to the Gagliardo-Nirenberg inequalities. And then move towards something which is more directly connected with the purpose of this lecture, which is first an asymptotic time layer, which is based on a spectral gap, so a linearization for large time asymptotics, an initial time layer where you use really nonlinear entropy methods to get a control, and then you have to glue these two layers, and this is the role of the threshold time. So the core of the proof is actually how to get this threshold time, and this is based on the uniform convergence in relative error for the solution of the fast diffusion equation, and it relies on detailed version of Harnack inequality, and I'm going to try to explain this a little bit more in details. So before going to the introduction, I would like to present my co-authors. These results have been obtained in collaboration with Matteo Bonforte, and this is a project that we started almost 10 years ago. Bruno Nazare, who was a colleague of mine at that time, was also involved from the very beginning. And Nikita Simonov, who recently defended his PhD, became part of the project a bit more recently, but he has been working really hard on this project. So, okay, so let me start with an introduction to the stability in Gagliardo-Nirenberg inequalities. So I will first specify which Gagliardo-Nirenberg inequalities I'm interested in, explain what are the optimal functions, and then what kind of stability result we can obtain. So here we are going to study this very special family of Gagliardo-Nirenberg inequalities, which is shown here on the screen. So it's an interpolation inequality in which you interpolate an L2p norm between the LP plus 1 norm and the L2 norm of the gradient on the Euclidean space RD. Dimension is going to be 1, 2, or 3 and higher. And of course, this is a special case of the Gagliardo-Nirenberg inequalities. The exponent theta, which shows up in the left-hand side, is fixed by the scaling property, so there is no choice, and this is the quantity which is shown here. And you easily recover it by just scaling an arbitrary function. Now, concerning the exponent p, there is some discussion. So first, in the higher dimensions, the exponent, d larger or equal than 3, then the exponent ranges between 1 and d over d minus 2. But remember that on the right-hand side here, you have a power 2p. So it corresponds to the critical Sobolev exponent. And of course, when you go to the limiting case of p equal d over d minus 2, then the inequality degenerates into the standard classical Sobolev inequality, which is here. And it corresponds, you can check it, to theta equal 1. Okay, so that the LP plus 1 term disappears here. On the other hand, of the interval, when p goes to 1, you can observe that the LP plus 1 norm goes to the L2 norm, the L2p norm also goes to the L2 norm. So p plus 1 and 2p go to 1, the constant goes to 1, theta goes to 0, And then you just have, when passing to the limit, L2 norm equal L2 norm, which is not very interesting. But since you have an equality at the limit, you can divide by p minus 1. And when you do that, what you obtain is the Euclidean logarithmic Sobolev inequality in the scale invariant form, which was found by Blackman and Stamm. And actually, it appears really in this form in the paper of Stamm here. And it was also recovered by Weissler using the scaling properties of the gross Sobolev inequality, logarithmic Sobolev inequality. Okay, so this is the endpoint. So just to summarize, this family of Gagliardo-Nirenberg inequalities interpolates between the Euclidean logarithmic Sobolev inequality for p equal 1 and in dimension higher or equal than 3, the Sobolev inequality. Now in dimension 1 and 2, there is no real limitation, and you can take an arbitrary exponent between 1 and plus infinity. Okay, so the good point of this inequality is that actually you know some optimal function, and this is something I discovered with Manuel Del Pino quite long ago. And they are of Aubin-Talenti type, in the sense that if you put the limiting exponent d over d minus 2 in dimension higher or equal than 3, you exactly recover the Aubin-Talenti function, which is optimal for the Sobolev inequality in dimension higher or equal than 3. However, it is also true for any exponent p between 1 and this p star, this limiting p star. And of course, the inequality one has a scaling invariance, translation invariant, and it is homogeneous. So any of a transformation of this function by when you multiply by a constant here, or when you scale by a parameter lambda, or when you translate by some parameter y, some vector y in Rd, is also going to be optimal. Okay, well, actually the result I obtained with Manuel in 2002 is that there are no other optimizers. So the equality case is realized if and only if the function g is one of these functions which are here and which generate a d plus 2-dimensional manifold. Now for a purpose, it's quite interesting to consider not the scale invariant form, but a form in which you make the sum of the L2 norm to the power to the 2 and the LP plus 1 norm to the power p plus 1. And by doing this, you fix a scale, and then it takes a different form, which is written here. And if you choose the specific coefficients, which are shown here, the a and the b, which are here, then you can check that g is an optimal function. So this is the scale which corresponds to this special g, which is here. And you have an expression of the optimal constant, which is expressed in terms of an integral of g, which is given here. And again, if you take the limit as p goes to 1 and take the appropriate derivative, then you recover the Euclidean logarithmic Sobolev inequality, but now in the non-scale invariant form. So it is the standard form of found by Gauss, which is here. Okay, so all this is quite consistent. Now, in the non-scale invariant form, you can make the difference of the two sides of the inequality, and that's what we are going to call the deficit functional. So you know that this deficit functional delta of f is going to be equal to 0 if and only if f is one of this function in the d plus 2-dimensional manifold of Aubin-Talenti type functions. And the question you want to try to answer is, how does this functional delta of f control the distance to the manifold? So there are some answers, and it's not a complete answer. First of all, in the critical case, there is the famous paper of Bianchi and Egnell, which says that for the critical exponent in dimension bigger or equal than 3, the difference of the two sides of the Sobolev inequality with the optimal constant SD actually controls the H10 distance to this manifold of the Aubin-Talenti function with some constant C, which is obtained here by an argument by contradiction, so no explicit value is known. if you abandon this strong norm and take a weaker norm, then you can produce some result. And here is an example that I obtained with Gaspar-Jankowiak. So still in dimension bigger or equal than 3. On the left-hand side, you consider still the Sobolev, the difference of the two terms in the Sobolev inequality. And it's well known that by duality, by Legendre duality, this Sobolev inequality is equivalent to the Hardy-Littlewood-Sobolev inequality, which corresponds to this right-hand side here. So this quantity being non-negative is exactly the HLS inequality with the same constant SD showing up here. And the result we obtained is that there is some constant C, which is here, such that you can use the HLS functional, the difference of the two terms, the HLS deficit, to control from below the Sobolev deficit up to a term that you need for homogeneity reason, which is here, with the Sobolev constant showing up here, and for some constant C, which is between 1 and 1 plus 4 over D. Okay, so it is, with 1, this is rather easy to obtain. Actually, you can do a kind of expansion of a square with a clever choice of the normalizations. And to get the 4 over D, which is here, you need to work a bit harder and you use flow, but this is another story. And there are various other improvements that you can obtain. Okay, various other cases that you can cover, especially in the subcritical case using entropy method. So I don't detail them, they are here because you will see them a bit later. So a very important quantity for our method is going to be the entropy, the relative entropy. I mean the relative entropy with respect to a given Aubin-Talenti type function. So it's this functional E of f, which is a convex functional such that it is equal to 0 if and only if f is equal to g. So I pick a specific g here. And the result is that the deficit functional in the Gagliardo-Nirenberg inequality, which is here, is actually can be estimated from below by the relative entropy, which is here. And of course, to do this, you have to fix the invariances. So you fix the mass of the function to be the same as the mass of the Aubin-Talenti function. You fix the center of mass to be at 0 to kill the translation invariance. Okay, and by doing that, then you can prove this result for some constant C, which is going to be explicit. So we don't claim at all any kind of optimality here. The estimate we get is very poor, but the purpose of my talk is to show that you have some explicit constant. There are some assumptions, and there are two parameters. One is that you have to define a neighborhood in relative entropy. So this is estimated, which is here, and the constant C is going to depend on G. And the other constraint that you have is that you need a certain decay of the function at infinity. So when you look at the L to P norm outside of a big ball of radius r and let r go to infinity, what you need is to have this decay rate, which is here. Okay. So as I mentioned to you, the constant C is explicit, and this is something on which I would like to insist a little bit. First of all, if you are an applied mathematician and interested in application of math, the standard question that somebody outside of mathematics would ask you is, how big is your constant? Or how do I estimate a rate of convergence? And you will see that it's equivalent. And I think that as applied analysts, this is a question we cannot leave completely unanswered. The other reason, and it's a more mathematical reason, is that by constructing the constant, it forces you to enter in the machinery of the estimate. And personally, at least, I understand much better the problem in that way, because by constructing the estimates, I know where the abstractions are, where are the limitations for the method or for the result. And also, on the way, it raises plenty of qualitative questions, which I find very interesting. Okay, so now you may wonder what the relative entropy is controlling. So here is at least a partial answer. It's not a distance, but it controls a distance at least of the function raised to the power 2p. And you have the famous Chisar-Kullback inequality. Actually, Chisar-Kullback is for the logarithmic case, so the limit case corresponding to p equal to 1. And it is a generalization which tells you that the square root of the relative entropy here controls with an explicit constant, depending on p, the distance in L1 to the orbital type function raised to the power 2p. And of course, you have to pick the right orbitality function. So you have to take the one with the same mass here. So now I should try to make a review of the literature, and the problem is that it touches various areas of mathematics, so it's very difficult to give, not to offend anybody, especially many collaborators and friends. So here I listed a number of papers which I consider as entry points in this literature. For instance, Bresis and Lieb, who were the first to ask the question answered by Bianchi and Egnell, but just consider these papers as entry point in this literature. A lot has been done using symmetrization, so it's quoted at the end of the page. And there are other issues which are connected with this. For instance, Alessio Figali has been working a lot on this stability issue for various related problems, and he has produced a number of very interesting results himself and with his collaborators. So some are listed here. Again, this is not complete. And it has links with gradient flows. This is something I will definitely not really mention here, although it goes through the fast diffusion flow, and I'm going to speak of the fast diffusion flow a lot. A very inspiring source of ideas was the Carré-Duchamp method, which was developed mostly for Markov processes and in semigroup theory. And for this, I would simply recommend to have a look at the book of Bacri, Gentil, and Ledoux, which summarizes a lot of things. And if you are interested in a more PDE point of view on Carré-Duchamp method and entropy method, I recommend the book by Ansgar Jungel, the lecture notes by Ansgar Jungel. A very important thing, of course, for our approach is going to be the global Harnack principle, which is mentioned here. And instead of entering in the details, I would like just to mention a few people to whom I'm really indebted for this story, and my co-authors as well. For instance, Manuel Del Pino, with whom I started this business on Gagliardo-Nirenberg inequalities 20 years ago, and I learned a lot from him. Giuseppe Toscani, who brought several tools from the Markov processes and information theory into the community of PDE analysts and brought the attention to very interesting problems and results. Alessio Figali, I already mentioned him. Juan Luis Vasquez is probably the person who convinced me of the beauty of the fast diffusion equation. And I would like to mention one more. It's Dominique Bacri for his explanation on the Carré-Duchamp and very enlightening discussion I had with him. For instance, that Gagliardo-Nirenberg inequalities are just kind of Sobolev inequalities in a higher dimension, and how you can change the dimension, but it's again another story. Anyway, now I'm going to focus on the fast diffusion equation, which is mentioned at the bottom of the page, because this is the key tool for our approach. And I will mention a few more references on the way. So, okay, let me pay attention to the time. Okay, so the fast diffusion equation, I'm going to consider this equation written on RD for some exponent m, which is between 0 and 1, and there will be a further restriction. And let me go directly to these Rényi entropy powers, which explain a little bit what are the ideas behind the Carré-Duchamp method. Okay. So to start with, I need a few notations. First of all, the fast diffusion equation, at least for m close enough to 1, preserves the mass. And I'm going to assume that I have an initial datum in L1 and that the mass is preserved, and it is going to be this M that we will fix later. To develop an entropy method, I also need to have the second moment finite, and this is very standard. Now, it's well known from the 70s that there are some self-similar solutions of the fast diffusion equation, which are known as the Barenblatt or Barenblatt-Patel solution, and they are just shown here. So there is a specific dependence as a power in the time variable. This solution play a little bit the role of a green function. They start as a delta and they capture the asymptotic behavior of the solution, even if the problem is nonlinear. Now, what matters for me is the profile here, and you already recognize something which looks like this augmented function, except that the power is not the same here. With this entropy, with this Barenblatt function, well, okay, one second. First, you have to define the entropy, and typically the entropy is the integral of u to the m, but be careful, remember that m is less than 1, so you have to be a bit careful with the meaning of it. So here it's a convex functional of u, sorry, concave functional of u. And another quantity which is completely essential is the Fisher information, which is here. Which is essentially the square of the gradient of the pressure variable here up to a factor u, which is in front. And the only thing actually that you have to remember is that the time derivative when u is a solution, the time derivative of the entropy when u is a solution is proportional to the Fisher information, which is this relation. Now, entropy powers were introduced in information theory with a number of objectives, and here it's a nonlinear version of the theory in which you consider a power of the entropy, and this power is just chosen in such a way that the if you plug the self-similar Barenblatt solution, then f has a linear growth. Now there is a very nice computation, which is essentially the result of the Carré-Duchamp method, which says, okay, I want to control the entropy or the Rényi entropy power in terms of the Fisher information. Let me take one more derivative. So I'm computing a second derivative of the entropy, or actually the first derivative of the Fisher information. And so I directly jump to the result. You can write it as a sum of two squares. Here, is the square of a matrix, the Hessian matrix of the pressure variable P up to a prefactor, which is here. And by square of the square of a matrix, I mean the sum of the square of each of the elements of the matrix. And this is a term that actually we drop. And there is another term, which is the Laplacian of the pressure variable to the square here, with a coefficient in front, which is m minus m1, and m1 is in the range d minus 1 over d to 1, which is shown here. And this is a limitation that we are going to assume from now on. Now, when you do this computation, you have to be a bit careful, and there are many integration by parts that you have to justify, and this is not an easy result. So let's consider this as a formal result for the moment. Now, Giuseppe Toscani and Giuseppe Savary noted in 2014 that the Rényi entropy power is a concave function, so which corresponds to this, which has a linear growth when you evaluate it on the Barenblatt self-similar solutions. And this Barenblatt self-similar solution attracts all the other solutions. So the Rényi entropy power is a concave function which is asymptotically a line, and this line is going to be given by the Barenblatt solutions. Now, when you evaluate it on a self-similar Barenblatt solution, well, there is a nice scaling. Sorry, when you evaluate the slope, well, the slope is a constant. It doesn't depend on time anymore, and it's given by this quantity evaluated just on the profile. You can get rid of the time dependence just by scaling. So the concavity property tells you that the slope, the derivative of the Rényi entropy power, which is shown here, well, it's decaying. Its limit is given by the Barenblatt, so you get an inequality. Now, when you write what it means, it's exactly the Gagliardo-Nirenberg Sobolev inequality written in the scale invariant form, which is here. And the way you go from the fast diffusion equation to the Gagliardo-Nirenberg inequality is just by taking u to the m minus 1/2 equal to f up to some normalization, or actually f to the p is equal to u, where p is this exponent. So I will have actually one more restriction, which is to take m bigger than 1/2, because I'm interested here only in positive exponents. Okay, and here's the condition which is here. Okay, and I will assume that it holds true until the end of the talk. Actually, this restriction enters only in dimension 1. Okay, now there is a more standard way of explaining the entropy methods and to relate them with the Gagliardo-Nirenberg inequalities. So it goes through the self-similar change of variable, which is shown here. And this is just the change of a variable which makes the Barenblatt self-similar solution constant, or at least asymptotically constant. Actually, it's very convenient, instead of taking t to the power 1 over mu as in the Barenblatt function, to take a solution of t's ODE, which is here. So it's just a power of r. But if you take r of 0 equal to 1, you preserve the initial data. So what you do is you transform your problem originally written in U into a problem written in terms of V. And now V solves a fast diffusion equation with harmonic potential. So this is this term which is here. Okay, and the advantage of this term is that now the self-similar profiles are changed into just a Barenblatt profile, and they are constant solution. So if you want to study the large time asymptotics, you do the change of variable, and now you study the convergence towards these stationary Barenblatt solutions. Okay, so the right tool to do this is now the relative entropy, now written in terms of this function v, and it takes this form v to the m minus b to the m minus m b to the m minus 1 v minus b, and it's not hard to convince you that it's going to be a quantity with a sign. Of course, you want also to introduce the generalized Fisher information, which is the time derivative of the entropy or the relative entropy, and this is this relative Fisher information, which is here. Okay, so the main result I found in 2002 with Manuel was the fact that the relation between the entropy and the Fisher information, which is this one, is actually exactly equivalent to the Gagliardo-Nirenberg inequalities. If you look a little bit more carefully to this, so the Fisher information is written on the left here, you have it here. And you see that when you expand the square, you get a Vx square times a constant, which is 4 here, the square of 2, which exactly cancels the 4 times x squared, which is here. So actually, written with this constant 4, there is no x-dependent terms. The cross term in the square of Fisher disappears by integration by parts. And now it's not very difficult to convince yourself that you just have the L2 norm of the gradient of V to the m minus 1/2, the L1 norm of V, and the integral of V to the power m. And by scaling, you get the Gagliardo-Nirenberg inequality, and it is equivalent. Now, written in terms of the flow, there is this interesting property that you have an exponential decay of the relative entropy with a rate here, which is exactly -4. This 4 is, of course, the 4 which is here, and it gives you the optimal constant in the Gagliardo-Nirenberg inequality if you write the details. So far, so good. So here is how you would prove it. So it's based on the Carré-Duchamp method, and it was something that was developed by Carriot and many of his co-authors. I don't want to go to the details. You have to, well, essentially redo the computation that you did for the Régnier entropy powers, but now with an x-dependent term. It's more complicated, but you have gained something. You have a stationary solution. So you have a way of truncating on large balls of radius r, taking the limit as r goes to infinity, and then get an actual proof without bothering with the boundary terms. There are also possibilities of improvement which are based on the fact that you can really use the remainder term in the Gagliardo-Nirenberg method. Is what is written here, but again, I don't want to go to the details. Anyway, this Gagliardo-Nirenberg method is very convenient to get results which are also valid in the nonlinear regime. But you can also investigate what happens asymptotically when you are close to a Harnack solution. So under two technical assumptions, which are here essentially to take care of arbitrary m's, here there is no limitation on the m, say positive, then you can get that the relative entropy, which is well defined in that case, is going to have some exponential decay, which is given here. So it is something that was done with Blanchet, Bonforte, Grillo, and Vasquez again some time ago. And the point is that by linearizing, you capture the optimal rate. So the optimal rate here, the optimal asymptotic rate, which is here, can be captured. And it's related with a spectral gap corresponding to this inequality, which shows up here in the RD Poincaré inequality, which is stated below. So it's a weighted Poincaré inequality, if you want. And there is an average condition, which is hidden here. Okay, so I don't want to, this is linear theory. It is something which has been discovered several times, for instance, by Denzler and Mike Kahn, but also by a student of Denis Bacri, Gregory Schaeffer. And you can study the spectrum. So this is my next slide, and I just show you the result. So you see here the game is to control the rate of decay of the entropy in terms of a rate, which is here. This rate is essentially the spectral gap. So this is the 8, which is here, okay? And you see you get minus 2t, at least in the range where m is between this m1 and 1 here, so in this range here. And 2 times 2 is the 4 that we had before. Actually, we didn't gain anything. Actually, we even lost because here you don't know what the constant is. What is interesting is that you can identify the eigenspace corresponding to this value here, and by fixing the center of mass at the origin, you kill this, and now you have an improved spectral gap which correspond to this. You go up to the blue line depending on m, so then you can gain something for the asymptotic time layer. I mean, when you are close, for large time evolution, when you are close enough to the Harnack solutions. Okay, so here is the detail of the statement. Allow me to skip it because time is running and I don't want to stay behind schedule. If you have questions, I can come back to this. So what we are going to use here is that this method, well, it has an absolutely major drawback. You rely on the linearized problem, so you need to have a control of the distance to the Barenblatt, and this is a strong control. So this is a control of the quotient of the solution with the Barenblatt solution. Okay, let me put something less aggressive here, like this. Okay, so V over B minus 1 is between minus epsilon and plus epsilon. So V over B has to be uniformly close to 1, and this is a very strong condition. Now, once you have this, then you can rely on the RD Poincaré inequality. And as I told you, well, you have the fact that you have to be in the kernel of the operator. So that's the standard things. It is the condition in the point. You have to remove the average in some sense. That's the Poincaré side of it. But if you put the additional condition that the center of mass is in appropriately weighted space is at 0, then what you get is that instead of having 4 here, you get a 4 alpha with an alpha which is strictly bigger than 1, at least in the range between m1 and 1. Okay, so this is the linear part, no condition, but when you want to apply it to a general function v, well, then you need to be in the correct neighborhood, and the condition is this one. So when you work out the details, you can replace the linearized free energy or entropy, which is here, by the nonlinear one up to an error term, the linearized Fisher information by the nonlinear one up to an error term. This error term is of course going to depend on the epsilon, which is here and here. And when you work out the details, what you find is that for some epsilon small enough, which is here, for some given eta, which is fixed here, there exists a chi, which has this expression here, and this is just an estimate. And if epsilon is in this range, then you have gained something. The quotient of the Fisher information by the entropy, I mean the nonlinear Fisher information by the nonlinear entropy, is now strictly bigger than 4 by some explicit constant. This is a gain in the rate, and this is going to be a gain in the optimal constant in the inequality, and this is going to be my stability result. So far, so good, but this is valid. You can expect this to be valid. Well, this is a stability result, but in a very strong neighborhood because of this relative uniform convergence that you need to impose. So to handle the nonlinear initial regime, you really need to rely on some nonlinear estimates that I'm not going to detail, but you have a very simple thing. The quotient of the Fisher information by the relative entropy, which is here, actually obeys to an ODE, which is written here. This is a consequence of the Carré-Duchamp method, so I don't show the details, but it's a simple ODE. And if at time capital T, you know that you have this, then you can rely on this differential inequality to build a backward in time estimate, which is here, and which is valid up to time t equals 0. So of course you lose on the constant. This constant is strictly, sorry, this constant here is strictly less than eta, but still it's a positive constant. So now you are able to connect the initial time layer where you have this deteriorated constant with the asymptotic regime in which you can rely on spectral consideration. The only point is to prove that there is some threshold time in which you can glue this initial time layer with the asymptotic time layer, and this is what we have to do now. And this is where the regularity theory for parabolic equation enters into the game. So our strategy is to fix some epsilon, which has to be taken small enough, but with a finite value that we can determine, get a threshold time in which we will have the relative uniform estimate. V divided by B minus 1 is in absolute value less than some epsilon. Okay, and this is this T star of epsilon, which is here. And the game is again to have something which is constructive here. And then using the spectral gap and spectral theory, we have this forward estimate, which tells us that for the corresponding eta, the quotient is bigger than 4 plus eta, so up to infinity, which is okay. So this is the asymptotic time layer. Okay, and using the backward in time estimate, get some deteriorated constant, but which is still strictly above 4 to connect from 0 to plus infinity. And now with something which is standard in Carré-Duchamp method is you apply this to an initial datum, you get an estimate using this backward in time estimate, you get it at time equals 0, and this is the functional inequality that you wanted to prove. So let me give you a more precise statement about this threshold time and how you built it. So what we have to build is this estimate, sorry, here, which tells you that you have some uniform in X estimate for any time large enough, for an epsilon small enough given in advance. And that's where you are going to need some assumptions. So from now on, I assume that the mass is fixed. So this is, and I pick the Barenblatt with exactly the same mass. So B is the profile 1 plus x squared to the power 1 over m minus 1. And the game is to construct this T star as a function of epsilon of the initial relative entropy J, which might be big, and a decay estimate that we need to assume, which is this constant A, which shows up here. And actually, this is quite a restriction on the space of function on which we can get our estimates, but at least for our method, this is something which is going to be essential, and we don't see how we could avoid it. By our method, I'm not claiming that there is no stability result in a larger setting. Okay, a key tool is going to be some interpolation estimates. So now we are going to work on local set or get local estimates, as it is usual in parabolic regularity theory. So we need some interpolation inequalities with precise constants. So here you have just the H1 norm on the ball, and you want to control an LP norm. Well, the P actually is going to be this critical exponent. So it's a Sobolev, just the Sobolev inequality written on the ball, but with no boundary condition and just the H1 norm here. So in dimension bigger or equal than 3, PM is this. And in lower dimension, we have to use subcritical exponent, and we pick P equal 4 in dimension 2 and 4 over M in dimension 1. And actually, we can find what are the optimal constants for the Sobolev inequality or for the subcritical inequality in dimension 1. And in dimension 2, well, we have an estimate which is not very good, because you see it is the numerical value, and this is what you numerically compute as an optimal constant. Now, there are two parameters, Q and beta. I don't want to insist, but this is the kind of thing you have to use to get explicit estimates. Okay, so now let me go very quickly through the proof. I have shown some of the constants, trying to show up how they happen. So you have an upper bound, which is a Herrero-Pierre type lemma, except that you have to redo it because you want to know what is this constant K, which is here. And actually, it's related with the constant inequality. So for this relation, with plenty of numerical constant, which is shown below. Second local estimate that you want to use is a lower estimate. Again, this can be derived by standard method, except that the constants were not known from the literature. So this is the time you have to wait for, and it involves some kappa star, which is shown below, and some constant K, which is again shown below, and which involves the Herrero-Pierre constant, which is hidden here. Once you have this local estimate, you go to a global Harnack principle, which is you compare it with Barenblatt functions, but be careful, Barenblatt function with different masses. So there is a Barenblatt with a lower mass, which is above, and an upper mass, which is below. And this is the kind of estimate. Again, everything can be made explicit. It's a long story. Concerning the outer estimates, outside of a big ball, actually knowing the global estimates, the global Harnack principle that you had before, you can compare it with the Barenblatt with the same mass. And here I'm in the original variable, so the Barenblatt function depends on time. You have it from above and from below, outside big balls, which are shown here, and for time, which are large enough for both estimates. Well, the inner estimate now is the story of parabolic regularity, and this is the very tricky part where it uses Harnack's inequality written as in Moses' proof. Again, we need to make the constant explicit, which was not done in Moses' paper, and this is at least one of the expression that you can get. So the constant K, which is here, is given below here, okay? And it involves a constant in some interpolation inequality and an exponent theta, which appears in Moses' theory through the elder exponent, which is the regularity exponent that you deduce from the Harnack's inequality. So far, so good. Here is the constant and the interpolation inequality, which was part of the previous identity. Let me go very fast. And this is the kind of result you finally end up with. So for a given epsilon, small enough, so there is a limitation on the size of epsilon, which I don't want to give explicitly, you can show that there is a constant C star, which depends only on the parameters A and G, which define my set of functions and sorry, which only depends on the constant in the elliptic, sorry, the parabolic regularity theory of the previous slides. Okay, and which depends explicitly on the two parameters a and g. A is related with the decay of the function, and g is the size of the initial relative entropy, and it's shown up here. Okay, so I'm almost at the end. Now you have to reconnect with what I said on entropy methods. So you have to go to self-similar variables, which change from the function u, which solves the fast diffusion equation, to the function v, which solves the fast diffusion equation in self-similar variables. And once you have done that, you have gained this 4 plus zeta now term. Before we had just a 4. So the Fisher information is controlled from below by an improved constant times the relative entropy. And the expression of zeta, well, it's shown in terms of eta, which is here. And this eta can be computed from the t star using, well, the time estimate once you go to self-similar variable and various other computation that I don't want to show. Well, here is an expression, semi-explicit, and if you want to go to see the details, just go to the paper. Let me mention that you may think that the improvement we got is again in some weak norm, because the difference, the deficit that is on the left-hand side just control an entropy. But actually, once you have this, you can redistribute the coefficients. And by introducing the standard deficit, which is here, you actually control a distance in terms of relative Fisher information, which is, again, an L2 norm of the gradient. Okay, so let me just jump to my final slide and tell you that the limitation that I have on the A and the G are just for to state a simple result. If you make everything explicit, don't take into account the scalings and don't fix the mass, then you really have a fully detailed stability result for Gagliardo-Nirenberg inequalities, in the sense that, so it's the difference of the two terms here in the theorem, except that they are raised to the power 2 p gamma. And so it's equal to 0 if and only if f is an Dolbeault type function. And it controls an explicit entropy now, but this entropy has to be scaled, and is this very complicated expression, which is shown up here. Now, of course, it depends on the tail behavior of the function, which is measured by this a of f. And hidden behind this, there is a scaling, which is this lambda of f, but everything, again, is fully explicit. So this gives you an expression here, which is not really a constant, because it depends on the a and the initial entropy here. Actually, here it's written for the initial datum, and then I can forget about the evolution problem. Okay, so here are the references of the paper. Actually, we split it in two pieces. One is essentially what I have presented to you, and the other one, which is shown up here, is just some supplementary material for people who really want to see the detail and how to compute the constants. Well, okay, this was my last slide. Okay, so here I am in my university, feeling a little bit alone, but it was really nice to talk to you, and I hope to see you soon back in Paris. Okay, anyway, thank you very much for your attention, and again, hope to see you soon in Paris.